Okay, let's get started again. Okay, so welcome back to week 3 of CS224N. Okay, so we've got a bit of a change of pace today after week 2. So this week in week 3, we're actually going to have some human language. And so this lecture has no partial derivative signs in it. And so we'll be moving away from sort of working out the sort of technicalities of doing neural networks and backpropagation and the sort of math-heavy week 2. And so then this week what we actually want, well, in today's lecture we want to look at, well, what kind of structures do human language sentences have and how we can build models that build that kind of structure for sentences that we see. So first of all, I'm going to sort of explain and motivate a bit about structure of human language sentences. So that's kind of like linguistics in 20 minutes or something. Then going to particularly focus in on dependency grammars, and then going to present a method for doing dependency grammar parsing called transition-based dependency parsing, and then talk about how you can make neural dependency parsers. So going on, just a couple of announcements. So assignment 2 was due 1 minute ago. So I hope everyone succeeded in getting assignment 2 out of the way. If you're still working on it, do make sure to make use of the office hours and get help for that. Coming out just today is assignment 3. Assignment 3 is basically about this lecture. So in assignment 3, what you're doing is building a neural dependency parser. And so we hope that you can put together what you learned about neural networks last week and the content of today and jump straight right into building a neural dependency parser. The other thing that happens in assignment 3 is that we start using a deep learning framework, PyTorch. So for doing assignment 3, instruction 0, and this is in the PDF for the assignment, is to install PyTorch as a Python package and start using that. So we've attempted to make assignment 3 sort of be a highly scaffolded tutorial where you can start to learn how to do things in PyTorch by just writing a few lines of code at a time. Hopefully that works out for people. If you have any issues with that, well, obviously you can send Piazza messages, come to office hours. I mean, the one other thing you could think of doing is that there's sort of a 1-hour introduction to PyTorch on the PyTorch site where you've directed for installing PyTorch, and you could also look at that if that was maybe helpful. Other final mentions, so final projects, we're going to sort of focus on those more in week 5, but if it's not bad to be thinking about things you could do if you want to do a custom final project. You're certainly encouraged to come and talk to me or the TAs. We have under the sort of office hours page on the website a listing of the expertise of some of the different TAs. Since I missed my office hours yesterday, I'm going to have a shortened office hour tomorrow from 1 to 2:20. That's at the same time as the normal CS224N office hour, so you can kind of come for any reason you want, but it might be especially good to come to me if you want to talk about final projects. Okay. So let's leap in and start talking about the structure of sentences. And so I just sort of want to explain something about human language sentence structure and how people think about that structure and what kind of goals then people in natural language processing have of sort of building structure to understand the meaning of sentences. All of the examples I'm going to give today are in English because that's a language that you're all expected to have some competence in. But this really isn't meant to be sort of facts about English. This is meant to be sort of ideas of how you can think about the structure of human language sentences that are applied to all sorts of languages. Okay, and so in general, there are two different ways that linguists have thought about the structure of sentences. There's some relations to them. One of them is called phrase structure or phrase structure grammars. And if you vaguely remember from CS103, if you did that, when you spent about a lecture on context-free grammars, phrase structure grammars are using the tools of context-free grammars to put structures over sentences. And so I'm first of all going to just briefly introduce that so you've seen it, but actually the main tool that we're going to use in this class and for assignment 3 is to put dependency structures over sentences, so I'll then go about that. So the idea of phrase structure is to say that sentences are built out of units that progressively nest. So we start off with words, that, cat, cuddly, etc. And then we're going to put them into bigger units that we call phrases, like the cuddly cat by the door. And then you can keep on combining those up into even bigger phrases, like the cuddly cat by the door. Oops. Okay, that's that. So how does this work? Well, so the idea of it, and this is sort of the way a linguist thinks, is to say, well, here's this language, which, you know, might not be English, it might be Oaxacan or some other language. What kind of structure does it have? And well, we could look at lots of sentences of the language. And so the linguist is going to think, well, I can see patterns like the cat, our dog, our cat, etc. So it sort of seems like there's one word class here, which linguists often refer to as determiners. They're also referred to as articles sometimes in English. And there's another word class here of nouns. And so to capture this pattern here, it seems like we can make this unit that I see all over the place in language, which is made of a determiner followed by a noun. And so I'd write a phrase structure grammar rule, i.e. a context-free grammar rule of I can have a noun phrase that goes to a determiner and a noun. Okay, but you know, that's not the only thing that I can see. So I can also see other examples in my language of the large cat or a barking dog or the cuddly cat, the cuddly dog. So that seems that I need to put a bit more stuff into my grammar. So maybe I can say for my grammar that a noun phrase goes to a determiner, and then optionally you can put in an adjective, and then you can have a noun. And then I poke around a little bit further and I can find examples like the cat in a crate or a barking dog by the door, and I can see lots of sentences like this. And so I want to put those into my grammar. But at that point I noticed something special, because look, here are some other things, and these things look a lot like the things I started off with. So it seems like we're sort of having a phrase with the same expansion potential that's nested inside this bigger phrase, because these ones can also be expanded, right? I could have something like the green door or something in here. So I want to capture that in some way. So maybe I could say that a noun phrase goes to a determiner, optionally an adjective, a noun, and then a something else, which I'll call a prepositional phrase. And then I'm going to write a second rule saying that a prepositional phrase goes to a preposition, that's going to be these words here, followed by a noun phrase. And so then I'm reusing my noun phrase that I defined up here, and so then I could immediately generate other stuff. I can sort of say the cat by the large door, or indeed I could say the cat by the large crate, the cat by the large crate on the table, or something like that, because once I can have a prepositional phrase includes a noun phrase, and a noun phrase includes a prepositional phrase, I've already got something that I can kind of recursively go back and forth between noun phrases, and I can make infinitely big sentences, right? Yeah? Yeah? So I could write something like, yeah, the cat by the large crate on the large table by the door. Right, I can keep on going and make big sentences, and I could say, well, I don't have space to fit it on this slide, but I've got an analysis of this according to my grammar, where that's a noun phrase goes to determiner, noun, prepositional phrase. The prepositional phrase goes to a preposition and a noun phrase, and this noun phrase goes to determiner, adjective, noun, prepositional phrase, and that goes to a preposition and another noun phrase, and I keep on going, and I can produce big sentences. Okay, and you know, that kind of then continues on because you know, I can then start seeing more bits of grammar. So I could say, well, I can now talk to the cat, and so if I want to capture this talking to a cat here, well, that now means I've got a verb, because verbs like talk and walk are verbs, and then talk to the cat, it seems like after that could become a prepositional phrase, and so I could write another rule saying that a verb phrase goes to a verb followed by a prepositional phrase, and then I can make more bigger sentences like that. And I could look at more sentences of the language and start building up these context-free grammar rules to describe the structure of the language. And that's part of what linguists do, and different languages have different structures. So, for example, like in this little grammar I've had, and in general in English, what you find is that prepositional phrases follow the verb, but if you go to a different language like Chinese, what you find is the prepositional phrases come before the verb. And so we could say, okay, there are different rules for Chinese, and I could start writing a context-free grammar for them. Okay, beauty. So that's the idea of context-free grammars. And actually, you know, this is the dominant approach to linguistic structure that you'll see if you go into a linguistics class in the linguistics department. People make these kind of phrase structure grammar trees. But just to be contrary, no, it's not actually just to be contrary, it's because this alternative approach has been very dominant in computational linguistics. What I'm going to show you instead is the viewpoint of dependency structure. So the idea of dependency structure is, rather than having these sort of phrasal categories like noun phrases and prepositional phrases and things like that, we're going to directly represent the structure of sentences by saying how words are arguments or modifiers of other words in a recursive fashion, which is sort of another way of saying how they're dependents of other words. So we have a sentence, look in the large crate in the kitchen by the door, and if we want to, we can give these words word classes, so we can still say this is a verb and this is a preposition and this is a determiner and this is an adjective and this is a noun. But to represent the structure, what we're going to say is, well, look here is the root of this whole sentence, so that's where things start. And then, well, where we're going to look is in the large crate, so that is a dependent of look. And, well, then we have, for the crate, it's got some modifiers. It's a large crate, so that's a dependent of crate. It's the large crate, that's a dependent of crate. And in the system of dependencies I'm going to show you, we've got in as kind of a modifier of crate in the large crate. I could come back to that. Well, but this crate has its own modification because it's a crate in the kitchen. So we have in the kitchen as a modifier of crate, and it's the kitchen, in the kitchen. These are dependents of crate. And well, then we have this next bit, by the door, and as I'll discuss in a minute, well, what is the by the door modifying? It's still modifying the crate. It's saying it's a crate by the door. Okay, so that by the door is also a dependent of crate, and then we've got this structure of dependencies coming off of it. Okay, and so that's then the structure you get, maybe drawn a little bit more neatly when I did it in advance like this. And so we call these things a dependency structure. And so crucially, what we're doing here is that we're, sorry, I had two different examples. Whoops, different examples. What we're doing is saying what words modify other words. And so that allows us to sort of understand how the different parts of the sentence relate to each other. And so overall, you know, let me just sort of say, you know, you might wonder, why do we need sentence structure? You know, the way language seems to work when you're talking to your friends is that you just blabber something and they understand what you're saying, and what goes on beyond that is sort of not really accessible to consciousness. But, well, to be able to have machines that interpret language correctly, we sort of need to understand the structure of these sentences, because unless we know what words are arguments and modifiers of other words, we can't actually work out what sentences mean. And I'll show some examples of that as to how things go wrong immediately, because actually a lot of the time there are different possible interpretations you can have. And so in general, our goal is, you know, up until now, we've sort of looked at the meaning of words, right? We did word vectors and we found out words that were similar meaning and things like that. And you can get somewhere in human languages with just saying words. I mean, you can say hi and friendly and things like that. But you can't get very far with just words, right? The way human beings can express complex ideas and explain and teach things to each other is you can put together words to express more complex meanings, and then you can do that over and over again, recursively, to build up more and more complex meanings, so that by the time you're reading the morning newspaper, you know, most sentences are sort of 20, 30 words long, and they're saying some complex meaning like, you know, overnight Senate Republicans resolved that they would not do blah, 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 and you understand that flawlessly by just sort of putting together those meanings of words. And so we need to be able to know what is connected to what in order to be able to do that. And one of the ways of seeing that's important is seeing what can go wrong. Okay, so here is a newspaper article. San Jose cop kills man with knife. Now this has two meanings, and the two meanings depend on, well, what you decide depends on what, you know, what modifies what. So what are the two meanings? Meaning one. The cop stabs a guy. Right, so meaning one is the cop stabs a guy. So what we've got here is we've got the cops that are killing. So this is what we'll say is the subject of kill is the cops. And I'll just call them the San Jose cops here. And well, there's what they kill, which so the man is an object of killing. And then, well, one person is the cops use a knife to kill the person. And so that's then that this is a modifier, and, you know, if we're complex, we call it an instrumental modifier to say that the cops are killing people with a knife. That's one possible analysis. Okay, then there's a second meaning this sentence can have. The second meaning this sentence can have...
Man has a knife. Okay,
the second meaning the sentence can have is it's the man has a knife. So in that case, what we want to say is, well, no, it's this word man, and this man has a noun modifier, which is sort of saying something that the man possesses, and then this dependency is the same, and it's a man with a knife. Okay, and so the interpretations of these sentences that you can get depend on putting different structures over these sentences in terms of what is modifying what. Here's another one that's just like that one. Scientists count whales from space. Okay, so again, this sentence has two possible structures, right? That we have the scientists are the subject that are counting, and the whales are the object. And well, one possibility is that this is how they're doing the counting, so that they're counting the whales from space using something like a satellite. But the other possibility is that these parts are the same. This is the subject and this is the object, but these are whales from space, which, you know, we could have analyzed as a noun phrase goes to a noun and a PP in our constituency grammar, but as a dependency grammar, we're saying, oh, this is now a modifier of the whales, and that they are whales from space that are starting to turn up, as in the bottom example, right? So obviously what you want is this one is correct and this one is here wrong. And so this choice is referred to as a prepositional phrase attachment ambiguity, and it's one of the most common ambiguities in the parsing of English, right? So here's our prepositional phrase from space, and so in general when you have prepositional phrases and before it you have verbs and noun phrases or nouns, that the prepositional phrase can modify either of the things that come beforehand, right? And so this is a crucial way in which human languages are different from programming languages, right? In programming languages, we have hard rules as to how you're meant to interpret things that dangle afterwards, right? So in programming languages, you have an else is always construed with the closest if. Well, if that's not what you want, you have to use parentheses or indentation or something like that. I guess it's different in Python because you have to use indentation, but if we think of something like C or a similar language, right, if you haven't used braces to indicate, it's just deterministically the else goes with the closest if. But that's not how human languages are. Human languages are, this prepositional phrase can go with anything preceding, and the hearer is assumed to be smart enough to work out the right one. And, you know, that's actually a large part of why human communication is so efficient, right? Like, we can do such a good job at communicating with each other because most of the time we don't have to say very much, and there's this really smart person on the other end who can interpret the words that we say in the right way. So that's where if you want to have artificial intelligence and smart computers, we then start to need to build language understanding devices who can also work on that basis, that they can just decide what would be the right thing for from space to modify. And if we have that working really well, we could then apply it back to programming languages, and you could just not put in any braces in your programming languages, and the compiler would work out what you meant. Okay, so this is prepositional phrase attachment. It sort of seems, you know, maybe not that hard there, but, you know, it gets worse. I mean, this isn't as fun an example, but it's a real example of a sentence from the Wall Street Journal, actually. The board approved its acquisition by Royal Trust Co. Limited of Toronto for $27 a share at its monthly meeting. Boring sentence. But what is the structure of this sentence? Well, you know, we've got a verb here, and we've got exactly the same subject, and for this noun, object coming after it. But then what happens after that? Well, here we've got a prepositional phrase, here we've got a prepositional phrase. We've just got to see 4 prepositional phrases in a row. And so, well, what we want to do is say for each of these prepositional phrases what they modify. And starting off, there are only 2 choices, the verb and the noun proceeding as before. But it's going to get more complicated as we go in because, look, there's another noun here and another noun here and another noun here. So once we start getting further in, there'll be more possibilities. Okay, so let's see if we can work it out. So by Royal Trust Co. Limited, what's that modifying? Right, it's the acquisition. So it's not the board approved by Royal Trust Co Limited, it's an acquisition by Royal Trust Co Limited. Okay, so this one is a dependent of the acquisition. Okay, now we want to do of Toronto, and we have three choices. It could be this, this, or this. Okay, so of Toronto is modifying... It's acquisition of Toronto? No, I think that's the wrong answer. Is there another guess for what of Toronto is modifying? Royal Trust Co, right. So it's Royal Trust Co Limited of Toronto. So this of Toronto is a dependent of Royal Trust Co Limited. And Royal Trust Co Limited, right, that's this, again, sort of this noun phrase. So it can also have modifiers by prepositional phrase. Okay, for $27 a share is modifying acquisition, right? So now we leap right back. Oops. I'm drawing this wrong. Now we leap right back, and it's now the acquisition that's being modified. And then finally, we have at its monthly meeting is modifying... Well, the approved, right? It's approved, yeah. It's approved at its monthly meeting. Okay, oops, I drew that one, oops, I drew that one the wrong way around with the arrow. Sorry, it should have been down this way. I'm getting my arrows wrong. Whoops. Okay, so that we've got this pattern of how things are modifying. And so actually, you know, once you start having a lot of things that have choices like this, you start having, if I want to put an analysis onto this sentence to work out the right structure, I have to potentially consider an exponential number of possible structures, because I've got this situation where for the first prepositional phrase, there were 2 places it could have modified. For the second prepositional phrase, there are 3 places it could have modified. For the fourth one, there are 5 places it could have multiplied. That just sounds like a factorial. It's not quite as bad as a factorial, because normally once you've leapt back, that kind of closes off the ones in the middle, and so further prepositional phrases have to be at least as far back in terms of what they modify. And so if you get into this sort of combinatoric stuff, the number of analyses you get when you get multiple prepositional phrases is this sequence called the Catalan numbers. But that's still an exponential series, and it's sort of one that turns up in a lot of places when there are tree-like contexts. So if any of you are doing or have done CS228, where you see triangulation of probabilistic graphical models, and you ask how many triangulations there are, that's sort of like making a tree over your variables, and that again gives you the number of them as the Catalan series. Okay, but so the point is we end up with a lot of ambiguities. Okay, so that's prepositional phrase attachments, a lot of those going on. They're far from the only kind of ambiguity, so I want to tell you about a few others. Okay, shuttle veteran and long-time NASA executive Fred Gregory appointed to board. Why is this sentence ambiguous? What are the different readings of this sentence? Yeah?
The veteran and Gregory are being appointed to the board, or Gregory is a veteran?
Okay, so great answer. So yeah, there are 2 possibilities, right? That is either that there's somebody who's a shuttle veteran and a long-time NASA executive, and their name is Fred Gregory, and that they've been appointed to the board, or the other possibility is that there's a shuttle veteran and there's a long-time NASA executive, Fred Gregory, and both of them have been appointed to the board. And so again, we can start to indicate the structure of that using our dependencies. So we can either say, okay, there's Fred Gregory, and then this person is a shuttle veteran and long-time NASA executive, or we can say, well, we're doing appointment of a veteran and the longtime NASA executive Fred Gregory. And so we can represent by dependencies these two different structures. Okay, that's one. That one's not very funny again. So here's a funnier example that illustrates the same ambiguity effectively. So here's President's first physical, doctor, no heart, cognitive issues. So there isn't actually an explicit coordination word here, but effectively in natural language, or certainly English, you can use kind of just comma of sort of list intonation to effectively act as if it was an and or an or. Right, so here we have again two possibilities, that either we have issues and the dependencies of issues is that there are no issues, so that's actually a determiner, no issues, and then it's sort of like no heart or cognitive issues. So heart is another dependent, it's sort of a noun compound, heart issues, and so we refer to that as an NN dependency, and then it's heart or cognitive. So that heart or cognitive is a conjoined phrase inside of this no heart or cognitive issues. But there's another possibility, which is that the coordination is at the top level, that we have no heart and cognitive issues. And at that point, we have the cognitive as an adjective modifier of the issues, and the no heart, the determiner is just a modifier of heart, and then these are being conjoined together. So heart has a coordinated dependency of issues. Okay, that's one. I've got more funny ones. Student gets, Okay, so what the person who wrote this intended to have is that here we've got an adjective modifier ambiguity. So the intended reading was that first is an adjectival modifier of first-hand, and it's first-hand experience. So the first hand is a modifier of experience, and the job is also a modifier of experience, and then we have the same kind of subject, object reading on that one. But unfortunately, this sentence has a different reading where you change the modification relationships, and you have it's the first experience, and it goes like this. Okay, one more example. Mutilated body washes up on Rio Beach to be used for Olympics beach volleyball. What are the two readings that you can get for this one? Okay, so we've got this big phrase that I won't try and put a structure over of, to be used for Olympic beach volleyball. And then, this is sort of like a prepositional phrase attachment ambiguity, but this time, instead of it's a prepositional phrase that's being attached, we've now got this big verb phrase, we call it, right? So that when you've sort of got most of a sentence but without any subject to it, that's sort of a verb phrase, to be used for Olympic beach volleyball, which might be in an infinitive form. Sometimes it's in participial form, like being used for beach volleyball. And really, those kind of verb phrases are sort of just like prepositional phrases. Whenever they appear towards the right end of sentences, they can modify various things like verbs or nouns. So here, we have two possibilities. So this to be used for Olympics beach volleyball, what the right answer is meant to be is that is a dependent of the Rio Beach. So it's a modifier of the Rio Beach. But the funny reading is that instead of that, we can have, here's another noun phrase, mutilated body, and it's the mutilated body that's going to be used. And so then this would be a noun phrase modifier of that. Okay, so knowing the right structure of sentences is important to understand the interpretations you're meant to get and the interpretations you're not meant to get. Okay, but it's sort of, okay, you know, I was using funny examples for the obvious reason, but you know, this is sort of essential to all the things that we'd like to get out of language most of the time. So, you know, this is back to the kind of boring stuff that we often work with, of reading through biomedical research articles and trying to extract facts about protein-protein interactions from them or something like that. So, you know, this is the results demonstrated that Chi-C interacts rhythmically with Sas-A, Chi-A, and Chi-B. And, well, whoops, I've got to turn those notifications off. So if we want to get out sort of protein-protein interaction facts, you know, well, we have this Chi-C that's interacting with these other proteins over there. And, well, the way we can do that is looking at patterns in our dependency analysis. And so that we can sort of see this repeated pattern where you have the noun subject here interacts with a noun modifier, and then it's going to be these things that are beneath that of the Sas-A and its conjoined things, Chi-A and Chi-B, are the things that it interacts with. So we can kind of think of these two things as essentially patterns. Oops, I actually misedited this, sorry. This should also be nmod with. Oops. We can kind of think of these two things as sort of patterns and dependencies that we could look for to find examples of just protein-protein interactions that appear in biomedical text. Okay. So that's the general idea of what we want to do. And so the tool we want to do it with is these dependency grammars. And so I've sort of shown you some dependency grammars. I just want to sort of motivate dependency grammar a bit more formally and fully, right? So dependency grammar postulates that what a syntactic structure is that you have relations between lexical items that are sort of binary asymmetric relations, which we draw as arrows because they're binary and asymmetric, and we call dependencies. And there's sort of two ways, common ways of writing them, and I've sort of shown both now. One way is you sort of put the words in a line, and that makes it easy to see the whole sentence, and you draw those sort of loopy arrows above them. And the other way is you sort of more represent it as a tree, where you put the head of the whole sentence at the top, submitted, and then you say the dependents of submitted are Bills, were, and Brownback, and then you say the dependents of each of those. So it was bills on ports and immigration, so they're dependents of bills, and were submitted, were as a dependent of submitted, and you're giving this kind of tree structure. Okay, so in addition to the arrows, commonly what we do is we put a type on each arrow which says what grammatical relation is holding them between them. So is this the subject of the sentence? Is it the object of the verb? Is it a conjunct and things like that? We have a system of dependency labels. So for the assignment, what we're going to do is use universal dependencies, which I'll show you a little bit more of in a minute. And if you think, man, this stuff is fascinating, I want to learn all about these linguist structures, there's a universal dependencies site that you can go off and look at and learn all about them. But if you don't think that's fascinating, for what we're doing for this class, we're never going to make use of these labels. All we're doing is making use of the arrows. And for the arrows, you should be able to interpret things like prepositional phrases as to what they're modifying, just in terms of where the prepositional phrases are connected and whether that's right or wrong. Okay, yeah, so formally when we have this kind of dependency grammar, we're sort of drawing these arrows and we sort of refer to the thing at this end as the head of a dependency and the thing at this end as the dependent of the dependency. And as in these examples, our normal expectation and what our parsers are going to do is that dependencies form a tree. So it's a connected, acyclic, single rooted graph at the end of the day. Okay, so dependency grammar has an enormously long history. So basically, the famous first linguist that human beings know about is Panini, who wrote in the 5th century before the Common Era and tried to describe the structure of Sanskrit. And a lot of what Panini did was working out things about all of the morphology of Sanskrit that I'm not going to touch at the moment. But beyond that, he started trying to describe the structure of Sanskrit sentences. And the notation was sort of different, but essentially the mechanism he used for describing the structure of Sanskrit was dependencies, of sort of working out these, what are arguments and modifiers of what relationships like we've been looking at. And indeed, if you look at kind of the history of humankind, most of attempts to understand the structure of human languages are essentially dependency grammars. Sort of in the later parts of the first millennium, there was a ton of work by Arabic grammarians, and essentially what they used is also kind of basically a dependency grammar. So compared to that, you know, the idea of context-free grammars and phrase structure grammars is incredibly, incredibly new. I mean, you can basically totally date it. There was this guy Wells in 1947 who first proposed this idea of having these constituents and phrase structure grammars, and where it then became really famous is through the work of Chomsky, which, love him or hate him, is by far the most famous linguist and also variously contributed to computer science. Who's heard of the Chomsky hierarchy? Do people remember that, 103? Yeah, okay, the Chomsky hierarchy. The Chomsky hierarchy was not invented to torture beginning computer science students. The Chomsky hierarchy was invented because Chomsky wanted to make arguments as to what the complexity of human languages was. Okay, yeah, so in modern work, there's this guy, Lucien Tainier, and he sort of formalized the kind of version of dependency grammar that I've been showing you, and so we sort of often talk about his work. And, you know, it's long-term been influential in computational linguistics. Some of the earliest parsing work in US computational linguistics was dependency grammars, but I won't go on about that more now. Okay, just two little things to note. I mean, if you somehow start looking at other papers where there are dependency grammars, people aren't consistent on which way to have the arrows point. There are sort of two ways of thinking about this, that you can either think, okay, I'm going to start at the head and point to the dependent, or you can say, I'm going to start at the dependent and say what its head is, and you find both of them. The way we're going to do it in this class is to do it the way Tainier did it, which was you start at the head and pointed to the dependent. Oh, sorry, I'm drawing that wrong. Whoops. Because discussion of the outstanding issues, so really the dependent is sort of discussion. Okay, but we go from heads to dependents. And usually it's convenient to sort of, in addition to the sentence, to sort of have a fake root node that points to the head of the whole sentence. And so we use that as well. Okay. So to build dependency parsers, or to indeed build any kind of human language structure finders, including kind of constituency grammar parsers, the central tool in recent work, where recent work kind of means the last 25 years, has been this idea of tree banks. And the idea of tree banks is to say we are going to get human beings to sit around and put grammatical structure over sentences. And so here are some examples I'm showing you from universal dependencies, where here are some English sentences. I think Miramar was a famous goat trainer or something, and some human being has sat and put a dependency structure over this sentence and all the rest. And with the name universal dependencies, this is just an aside, universal dependencies is actually a project I've been strongly involved with, but precisely what the goal of universal dependencies was is to say what we'd like to do is have a uniform parallel system of dependency description which could be used for any human language. So if you go to the universal dependencies website, it's not only about English. You can find universal dependency analyses of French or German or Finnish or Kazakh or Indonesian, lots of languages. Of course, there are even more languages which there aren't universal dependencies analyses of. So if you have a big calling to say, I'm going to build a Swahili universal dependencies tree bank, you can get in touch. But anyway, so this is the idea of tree banks. And, historically, tree banks wasn't something that people thought of immediately. This is an idea that took quite a long time to develop, right? That people started thinking about grammars of languages even in modern times in the 50s, and people started building parsers for languages in the early 1960s. And so there was decades of work in the 60s, 70s, 80s, and no one had tree banks. The way people did this work is that they wrote grammars, that they either wrote grammars like the one I did for constituency of noun phrase goes to determiner, optional adjective noun, noun goes to goat, or the equivalent kind of grammars in a dependency format, and they hand-built these grammars and then had parsers that could parse these sentences. And going into things, having a human being write a grammar feels more efficient, because if you write a rule like noun phrase goes to determiner, optional adjective noun, I mean, that describes a huge number of phrases, well actually an infinite number of phrases, so that, this is the structure of, the cat, the dog, a cat, a dog, a large dog, all those things we saw at the beginning. So it's really efficient, you're capturing lots of stuff with one rule. But it sort of turned out that in practice that wasn't such a good idea, and it turned out to be much better to have these kind of tree banks of putting structures over sentences. And it's sort of a bit more subtle as to why that is, because it sounds like pretty menial work building tree banks, and in some sense it is. But, it turns out to be much more useful. I mean, so one huge benefit is that tree banks are very reusable. That effectively what there was in the 60s, 70s, and 80s was that every different NLP person who set about building a parser invented their own notation for grammar rules, which got more and more complex, and it was only used by their parser and nobody else's parser, and so there was no sharing and reuse of the work that was done by human beings. Where once you have a tree bank, it's reusable for all sorts of purposes, that lots of people build parsers from it, but also other people use it as well. Like linguists now often use tree banks to find examples of different constructions. But beyond that, this sort of just became necessary once we wanted to do machine learning. So if we want to do machine learning, we want to have data that we can build models on. And in particular, a lot of what our machine learning models exploit is how common are different structures. And so we want to know about the commonness and the frequency of things. But then tree banks gave us another big thing, which is, well, lots of sentences are ambiguous, and what we want to do is build models that find the right structure for sentences. And if all you do is have a grammar, you have no way of telling what is the right structure for ambiguous sentences. All you can do is say, hey, that sentence with 4 prepositional phrases after it that I showed you earlier, it has 14 different parsers. Let me show you all of them. But once you have tree bank examples, you can say this is the right structure for this sentence in context, and so you should be building a machine learning model which will recover that structure, and if you don't, that you're wrong. Okay, so that's tree banks. So how are we going to build dependency parsers? Well, somehow we want models that can kind of capture what's the right parse. And just thinking about abstractly, you know, there's sort of different things that we can pay attention to. So one thing that we can pay attention to is the sort of actual words, right? Discussion of issues, that's a reasonable thing. So it's reasonable to have issues as a dependent of discussion, where, you know, discussion of outstanding, that sounds weird, so you probably don't want that dependency. There's a question of how far apart words are. Most dependencies are fairly short distance, though not all of them are. There's a question of what's in between. If there's a semicolon in between, there probably isn't a dependency across it. And the other issue is sort of how many arguments do things take. So here we have was completed. If you see the words was completed, you sort of expect that there'll be a subject before it of something was completed, and it'd be wrong if there wasn't. So you're expecting an argument on that side. But on the other hand, it won't have an object after it. You won't say the discussion was completed, the goat. That's not a good sentence, right? So you won't have an object after it. So there's sort of information of that sort. And we want to have our dependency parsers be able to make use of that structure. Okay. So effectively what we do when we build a dependency parser is we're going to say for each word it is going to be the dependent of some other word or the root. So this give here is actually the head of the sentence, so it's the dependent of root. The talk is a dependent of give. Art is a dependent of talk. And so for each word, we want to choose what it is a dependent of. And we want to do it in such a way that the dependencies form a tree. So that means it'd be a bad idea if we made a cycle. So if we sort of said bootstrapping was a dependent of talk, but then we had things sort of move around, so this goes to here, but then talk's a dependent of that, and it's all in a cycle. That's bad news. We don't want cycles, we want a tree. And there's one final issue, which is we don't want things that is to whether we want to allow dependencies to cross or not. And this is an example of this. So most of the time, dependencies don't cross each other, but sometimes they do. And this example here is actually an instance for that. So I'll give a talk tomorrow on bootstrapping. So we're giving a talk, that's the object, and when it's being given is tomorrow. But this talk has a modifier that's on bootstrapping. So we actually have another dependency here that crosses that dependency. And that's sort of rare. That doesn't happen a ton in English, but it happens sometimes in some structures like that. And so this is the question of whether, what we say is that the parse of a sentence is projective if there are no crossing dependencies, and it's non-projective if there are crossing dependencies. And most of the time English is projective in its parses of sentences, but occasionally not. And when it's not is when you kind of have these constituents that are delayed to the end of the sentence, right? You could have said, I'll give a talk on bootstrapping tomorrow, and then it'd have a projective parse. But if you want to, you can kind of delay that extra modifier and say, I'll give a talk tomorrow on bootstrapping, and then the parse becomes non-projective. Okay, so that's that. There are various ways of doing dependency parsing, but basically what I'm going to tell you about today is this one called transition-based or deterministic dependency parsing, and this is the one that's just been enormously influential in practical deployments of parsing. So when Google goes off and parses every web page, what they're using is a transition-based parser. And so this was a notion of parsing that was mainly popularized by this guy, Joachim Nievre, who's a Swedish computational linguist. And what you do is it's sort of inspired by shift-reduce parsing. So probably in, CS123 or compilers class or something, you saw a little bit of shift-reduce parsing. And this is sort of like a shift-reduce parser, apart from when we reduce, we build dependencies instead of constituents. And this has a lot of very technical description that doesn't help you at all to look at in terms of understanding what a shift-reduce parser does. And here's a formal description of a transition-based shift-reduce parser, which also doesn't help you at all. So instead, we're going to look at this example because that will hopefully help you. So what I want to do is parse the sentence, "I ate fish." And formally what I have is I have a way I start, there are 3 actions I can take, and I have a finish condition for a formal parse. And so here's what I do. So I have a stack, which is on this side, and I have a buffer. So the stack is what I have built, and the buffer is all the words in the sentence I haven't dealt with yet. So I start the parse, and that's this sort of instruction here, by putting my root for my whole sentence onto my stack, and my buffer is the whole sentence, and I haven't found any dependencies yet. Okay, and so then the actions I can take is to shift things onto the stack or to do the equivalent of a reduce where I build dependencies. So starting off, I can't build a dependency because I only have root on the stack, so the only thing I can do is shift. So I can shift I onto the stack. Now I could at this point say, let's build a dependency, I is a dependent of root, but that would be the wrong analysis because really the head of this sentence is 8, so I'm a clever boy and I shift again, and now I have root I8 on the stack. Okay, and so at this point, I'm in a position where, hey, what I'm going to do is reductions that build structure, because look, I have I8 here, and I want to be able to say that I is the subject of dependency of 8, and I will do that by doing a reduction. And so what I'm going to do is the left arc reduction, which says, look, I'm going to treat the second from top thing on the stack as a dependent of the thing that's on top of the stack. And so I do that, and so when I do that, I create the second from the head thing as a subject dependent of 8, and I leave the head on the stack 8, but I sort of add this dependency to the dependencies I've built. Okay, so I do that. Now I could immediately reduce again and say 8 is a dependent of root, but my sentence is actually I ate fish. So what I want to do is say, oh, there's still fish on the buffer. So what I should first do is shift again, have root 8 fish in my sentence, and then I'll be able to say, look, I want to now build the thing on the top of the stack as a right dependent of the thing that's second from top of the stack, and so that's referred to as a right arc move. And so I say right arc, and so I do a reduction where I've generated a new dependency, and I take the 2 things that are on top of the stack and say fish is a dependent of 8, and so therefore I just keep the head, I always just keep the head on the stack, and I generate this new arc. And so at this point, I'm in the same position. I want to say that this 8 is a right dependent of my root, and so I'm again going to do right arc and make this extra dependency here. Okay, so then my finished condition for having successfully parsed the sentence is my buffer is empty and I just have root left on my stack, because that's what I sort of said back here. That was buffer is empty as my finished condition. Okay, so I've parsed the sentence. So that worked well, but you know, I actually had different choices of when to shift and when to reduce, and I just miraculously made the right choice at each point. And well, one thing you could do at this point is say, well, you could have explored every choice and seen what happened and gone different parsers. And I could have, but if that's what I'd done, I would have explored this exponential sized tree of different possible parsers. And if that was what I was doing, I wouldn't be able to parse efficiently. And indeed, that's not what people did in the 60s, 70s, and 80s. Clever people in the 60s said, rather than doing a crummy search here, we can come up with clever dynamic programming algorithms, and you can relatively efficiently explore the space of all possible parsers. And that was sort of the mainstay of parsing in those decades. But when Joachim Nivre came along, he said, yeah, that's true, but hey, I've got a clever idea. Because now it's the 2000s and I know machine learning. So what I could do instead is say I'm at a particular position in the parse and I'm going to build a machine learning classifier, and that machine learning classifier is going to tell me the next thing to do. It's going to tell me whether to shift, left arc or right arc. So if we're only just sort of talking about how to build the arrows, there are just three actions: shift, left arc, or right arc. If we're also wanting to put labels on the dependencies and we have R different labels, there are then sort of 2R plus 1 actions, because you sort of left arc subject or left arc object or something like that. But anyway, there's a set of actions, and so you're going to build a classifier with machine learning somehow which will predict the right action. And Joachim Nivre showed the sort of slightly surprising fact that actually you could predict the correct action to take with high accuracy. So in the simplest version of this, there's absolutely no search. You just run a classifier at each step and it says, what you should do next is shift, and you shift. And then it says, what you should do is left arc, and you left arc, and you run that through. And he proved, well, he showed empirically that even doing that, you could parse sentences with high accuracy. Now, if you want to do some searching around, you can do a bit better, but it's not necessary, and we're not going to do it for our assignment. But so if you're doing this just sort of run classifier, predict action, run classifier, predict action, we then get this wonderful result, which you're meant to explain a bit on the assignment 3, is that what we've built is a linear time parser, right? That because we're going to be sort of, as we chug through a sentence, we're only doing a linear amount of work for each word. And that was sort of an enormous breakthrough, because although people in the 60s had come up with these dynamic programming algorithms for sentences were always cubic or worse. And that's not very good if you want to parse the whole web. Whereas if you have something that's linear time, that's really getting you places. Okay, so this is the conventional way in which this was done, was, you know, we have a stack. We might have already built some structure of working out something's dependent of something. We have a buffer of words that we don't deal with, and we want to predict the next action. So the conventional way to do this is to say, well, we want to have features. And well, the kind of features you wanted was sort of usually some kind of conjunction of multiple things. So that if the top word of the stack is good, and something else is true, right? That the second to stop word of the stack is has, and its part of speech is verb, then maybe that's an indicator of do some action. So it had these very complex binary indicator features, and you'd build you'd literally have millions of these binary indicator features, and you'd feed them into some big logistic regression or support vector machine or something like that, and you would build parsers. And these parsers work pretty well, but you sort of had these sort of very complex hand-engineered binary features. So in the last bit of the lecture, I want to show you what people have done in the neural dependency parsing world. But before I do that, let me just explain how you evaluate dependency parsers. And that's actually very simple, right? So what you do is, well, you assume, because the human wrote it down, that there's a correct dependency parse for a sentence. She saw the video lecture like this. And so these are the correct arcs. And to evaluate our dependency parser, we're simply going to say which arcs are correct. So there are the gold arcs. So there's a gold arc from 2 to 1, she saw subject, and there's a gold arc from 0 to 2, the root of the sentence. These are the gold arcs. If we generate a parse, we're going to propose some arcs as to what is the head of each word, and we're simply going to count up how many of them are correct, treating each arc individually. And there are two ways we can do that. We can either, as we're going to do, ignore the labels, and that's then referred to as the unlabeled attachment score. So here in my example, my dependency parser got most of the arcs right, but it got this one wrong. So I say my unlabeled attachment score is 80%, or we could also look at the labels, and then my parser wasn't very good at getting the labels right, so I'm only getting 40%. And so we can just count up the number of dependencies and how many we get correct, and that's our accuracy. And in the assignment, you're meant to build a dependency parser with a certain accuracy. I forget the number now we're saying. Some number, 80 something or something, that you're meant to get to. Okay, maybe I'll skip that. Okay, so now I want to sort of explain to you just a bit about neural dependency parsers and why they are motivated. So I'd mentioned to you already that the conventional model had these sort of indicator features of on the top of the stack is the word good, and the second thing on the stack is the verb has, or on the top of the stack is some other word, and the second top is of some part of speech, and that part of speech has already been joined with a dependency of another part of speech. People hand engineer these features. And the problems with that was these features were very sparse. Each of these features matches very few things. They match some configurations but not others, so the features tend to be incomplete. And there are a lot of them. There are commonly millions of features. And so it turned out that actually computing these features was just expensive, so that you had some configuration on your stack and the buffer, and then you wanted to know which of these features were active for that stack and buffer configuration. And so you had to compute features from it. And it turned out that conventional dependency parsers spent most of their time computing features that went into the machine learning model rather than doing the sort of shifting and reducing of just a pure parser operation. And so that seemed like it left open the possibility that, well, what if we could get rid of all of this stuff and we could run a neural network directly on the stack and buffer configuration? Then maybe that would allow us to build a dependency parser which was faster and suffered less from issues of sparseness than a conventional dependency parser. And so that was a project that Danchi-Chen and me tried to do in 2014, is to build a neural dependency parser. And, you know, effectively what we found is that that's exactly what you could do. So here are sort of a few stats here. So these are these same UAS and LAS. So MultParser was Joachim Nivre's parser that I was sort of showing before, and it got a UAS on this data of 89.8. but everybody loved it. And the reason they loved it is it could parse at 469 sentences a second. There had been other people that had worked out different, more complex ways of doing parsing with so-called graph-based dependency parsers. So this is another famous dependency parser from the 90s. So it was actually, you know, a bit more accurate, but it was a bit more accurate at the cost of being 2 orders of magnitude slower. And, you know, people had worked on top of that. So here's an even more complex graph-based parser from the 2000s. And, well, you know, it's a little bit more accurate again, but it's gotten even slower. Okay, so what we were able to show is that using the idea of instead using a neural network to make the decisions of Joachim-Nievers style shift-reduce parser, we could produce something that was almost as accurate as the very best parsers available at that time. I mean, strictly we won over here and we were a fraction behind on UAS. But, you know, it was not only just as fast as Nievers parser, it was actually faster than Nievers parser because we didn't have to spend as much time on feature computation. And that's actually almost a surprising result, right? It's not that we didn't have to do anything. We had to do matrix multiplies in our neural network. But it turned out you could do the matrix multiplies more quickly than the feature computation that he was doing, even though at the end of the day it was sort of looking up weights that went into a support vector machine. So that was kind of cool. And so the secret was we're going to make use of distributed representations like we've already seen for words. So for each word, we're going to represent it as a word embedding like we've already seen. And in particular, we are going to make use of word vectors and use them as the starting representations of words in our parser. But, well, if we're interested in distributed representations, it seemed to us like maybe you shouldn't only have distributed representations of words. Maybe it'd also be good to have distributed representations of other things. So we had parts of speech, like, you know, nouns and verbs and adjectives and so on. Well, some of those parts of speech have more to do with each other than others. I mean, in particular, most NLP work uses fine-grained parts of speech. So you don't only have a part of speech like noun or verb. You have parts of speech like singular noun versus plural noun. And you have different parts of speech for, you know, work, works, working, kind of the different forms of verbs are given different parts of speech. As well. So there are sort of sets of parts of speech labels that are kind of clusters. So maybe we could have distributed representations of parts of speech that represent their similarity. Why not? Well, if we're going to do that, why not just keep on going and say the dependency labels, they also have a distributed representation. And so we built a representation that did that. So the idea is that we have in our stack the sort of the top positions of the stack, the first positions of the buffer, and for each of those positions we have a word and a part of speech, and if we've already built structure as here, we kind of know about a dependency that's already been built. And so we've got a triple for each position, and we're going to convert all of those into a distributed representation, which we are learning, and we're going to use those distributed representations to build our parser. Okay, now so you know, starting from the next lecture forward, we're going to sort of start using more complex forms of neural models. But for this model, we did it in a sort of a very simple, straightforward way. We said, well, we could just use exactly the same model, exactly the same parser structure that Nivra used, right, doing those shifts and left arcs and right arcs. The only part we're going to turn into a neural network is we're going to have the decision of what to do next being controlled by our neural network. So our neural network is just a very simple classifier of the kind that we were talking about last week. So based on the configuration, we create an input layer, which means we're sort of taking the stuff in these boxes and looking up a vector representation for each one and concatenating them together to produce an input representation that's sort of similar to when we were making those window classifiers and we can concatenate a bunch of stuff together. So that gives us our input layer. So from there, we put things through a hidden layer, just like last week. We do wx plus b and then put it through a ReLU or nonlinearity to a hidden layer. And then on top of that, we're simply going to stick a softmax output layer. So we're multiplying by another matrix, adding another bias term, and then that goes into the softmax, which is going to give a probability over our actions as to whether to shift left arc or right arc, or the corresponding one with labels. And then we're going to use the same kind of cross-entropy loss to say how good a job did we do at guessing the action that we should have taken according to the tree bank parse of the sentence. And so each step of the shift-reduced parser, we're making a decision as what to do next, and we're doing it by this classifier, and we're getting a loss to the extent that we don't give probability 1 to the right action. And so that's what we did using the tree bank. We trained up our parser, and it was then able to predict the sentences. And the cool thing was that this had all the good things of Nivra's parser, but by having it use these dense representations, it meant that we could get greater accuracy and speed than Nivra's parser at the same time. So here are sort of some results on that. I mean, I already showed you some earlier results, right? So this was showing the fact that we're outperforming these earlier parsers basically. But subsequent to us doing this work, people at Google, these papers here by Weiss and Andor, they said, oh, this is pretty cool. Maybe we can get the numbers even better if we make our neural network bigger and deeper, and we spend a lot more time tuning our hyperparameters. Sad but true, all of these things help when you're building neural networks, and when you're doing your final project, sometimes the answer to making the results better is to make it bigger, deeper, and spend more time tuning the hyperparameters. They put in beam search, as I sort of mentioned. Beam search can really help. So in beam search, rather than just saying, let's work out what's the best next action, do that one and repeat over. You allow yourself to do a little bit of search. You sort of say, well, let's consider 2 actions and explore what happens.
Quick question. Do humans always agree on how to build these trees? And if they don't, what would be the accuracy or agreement of humans relative to those?
So that's a good question, which I haven't addressed. Humans don't always agree. There are sort of 2 reasons they can't agree, fundamentally. One is that the humans sort of mess up, right? Because human workers doing this aren't perfect. And the other one is they genuinely think that there should be different structures. So, it varies depending on the circumstances and so on. If you just get humans to parse sentences and say, well, what is the agreement and what they produced, maybe you're only getting something like 92%. But, if you then do an adjudication phase and you say, look at these differences, is one of them right or wrong? There are a lot of them where, one person is effectively saying, oh yeah, I goofed, wasn't paying attention or whatever. And so then what's the residual rate in which people actually disagree about possible parsers? I think that's sort of more around 3%. Yeah, but there certainly are cases, and that includes some of the prepositional phrase attachment ambiguities. Sometimes there are multiple attachments that sort of seem plausible. It's not really clear which one is right, even though there are lots of other circumstances where one of them is very clearly wrong. Yeah.
We could do much better.
There's still room to do better. I mean, at the unlabeled attachment score, it's actually starting to get pretty good, but there's still room to do better. Yeah. Yeah, so beam search. A final thing that they did was, that we're not going to talk about here, is this sort of more global inference to make sure it's sensible. And so that then led to Google developing these models that they gave silly names to, especially the parsemic parseface model of parsing. And so, yeah, so that sort of pushed up the numbers even further, so that they were sort of getting close to 95% unlabeled accuracy score from these models. And actually this work is kind of, you know, deep learning people like to optimize. This work has continued along in the intervening 2 years, and the numbers are sort of getting a bit higher again. But, you know, so this actually led to a sort of a new era of sort of better parsers, because sort of effectively this was the 90s era of parsers that was sort of, we were around 90%, and then going into this sort of new generation of neural transition-based dependency parsers, we sort of have gone down, that we've halved that error rate, and we're now down to sort of about a 5% error rate. Yeah, I'm basically out of time now, but you know, there is further work, including, you know, at Stanford, another student, Tim Dozad, has some sort of more recent work that's more accurate than 95%. Right? So we're still going on, but I think I'd better stop here today, and that's neural dependency parsing.